Alright, we are ready now to do an example where we get quadratic factors in the denominator. Take a look at what we have here. Numerator is degree 2, denominator is degree 3. We don't have to do any polynomial long division this time. Degree of the top is less than the bottom. We do have to factor the denominator now. This might be a little more challenging. Let's just write this out. See, how would we factor this denominator? Well, you would start with your greatest common factor and pull that out. But if you begin to look at the terms, the greatest common factor is just 1. So there's nothing other than 1 to factor out. So I have 4 terms. How would I factor? What's the method called that we would possibly use? It is grouping. We're going to use the factoring by grouping method. So remember, we talked about factoring way at the beginning, how important it is, and it comes up from time to time, and here's an example. So I'm going to group the first 2 terms and the second 2 terms, see if I can find a common factor in those. Here, the GCF between x cubed minus 7x squared is x squared, leaving x minus 7. Here, the common factor between 4x and negative 28 rather, is positive 4. Pulling that out leaves me x minus 7. And that's good, right? If I have that same factor left over, grouping works. I can factor that x minus 7 out of these 2 terms now, and I get x minus 7. What's left? X squared plus 4. Now, can I factor x squared plus 4? No. That right there is prime over the rational numbers. In fact, prime over the reals. Cannot factor x squared plus 4. You could factor x squared minus 4. That's the difference of squares, but the sum of squares does not factor. And so what we have then is our partial fraction decomposition, 6x squared minus 13x plus 9 over the factored form, x minus 7, x squared plus 4. Looks like what? I have one linear factor, gives me one fraction, right? Constant over a linear term. This is a one quadratic factor. So what do we have here? In the denominator, I have x squared plus 4. In the numerator, I'm going to have bx plus c. So there's a linear factor over that quadratic factor. So I need to find a, b, and c. Need to find a, b, and c. So what I'm going to do, I'm going to multiply by the least common denominator here. And when I do so, what do I get? 6x squared minus 13x plus 9 on this side. Over here, when I multiply by this denominator, the x minus 7's cancel, and I'm just left with the x squared plus 4. And over here, the x squared plus 4's cancel. I'm left with bx plus c times x minus 7. Okay, now, I've used 2 techniques in the last 2 videos. I've done the little shortcut and then the method of undetermined coefficients. I'm going to use both now. I have to use undetermined coefficients, you'll see. First of all, what's restricted down here? What value is restricted? What value of x can we not have? 7, right? If I divide by, if x is 7, 7 minus 7 is 0, I'd be dividing by 0. That's undefined. So what I'm going to do is I'm going to use that here, though, where x can be 7 in this equation, and find one of my values of a, b, or c. Notice that's the only restricted value, though, here, because x squared plus 4, that factor is always positive, right? It's always 4 or more, right? It's never going to be 0. So I just have one little shortcut. I'm going to let x equal 7. And when I do that, I get 6 times 7 squared minus 13 times 7 plus 9 on this side when I let x be 7. Here I get a 7 squared plus 4. But then when I plug in 7 here, this is 7 minus 7. This is 0. This whole term right here is 0, right? Gone to 0. What do we get here? If I do this arithmetic, I'll have you check and see that you get 212. 7 squared is 49 plus 4 is 53a. And if I solve for a, 212 divided by 53 is 4. So the value of a is 4. But now what about bx plus c? So I don't know what or what B and C are, rather. What about B and C? So I don't have a shortcut for that. So what I'm going to do is I'm going to rewrite, now that I know what A is, just rewrite this equation knowing what A is. A is what? 4. So just replace A with 4, and I still have the B and the C. Okay, so I would use the shortcuts as much as you can, and then when you're done, write in the values that you found, and whatever's left you'll do by the method of undetermined coefficients. So undetermined coefficient says what? I'm going to expand this out. I know the coefficients over here for x squared are 6, for x -13, and the constant term is 9. They have to match over here. So distributing the 4, I get 4x squared plus 16. And then here I've got to FOIL this out, right? Bx times x is bx squared. That's first. Outer, -7 times bx, -7bx. Inner is cx. And last, c times -7 is -7c. So I have to expand that out. Now I combine like terms. What are all my x squared terms? I have a 4, and then what? Plus b times x squared. What about my x terms? -7b plus c. And then what about my constant terms? I've got a 16, that's constant, no variable, and a -7c. There's no x variable, right? So again, we're putting them in terms of the variable x. So I need to put it in a polynomial in terms of x to match up. So now I match up, right? So what do I know? 4 plus b must be equal to 6. This coefficient has to be 6. And right away I say, hey, I know what b is. What is b? b must be 2. b must be 2. And now I can use either of the other two. In fact, I'm going to go back here and just say, hey, the constant term, 16 minus 7c, what does that have to equal? That has to equal 9. And so I have what? -7c is what? Subtracting 16 is -7. And so C is 1. I've got B and I've got C. Notice that this also tells us that this will work for the last requirement, and that is this coefficient has to be -13. Well, if you let B be 2, you get -14 plus C is 1. -14 plus 1 is -13. It satisfies all of those. So you should double check that. That should be true. Okay, but now I know A is 4, B is 2, C is 1, and so I can rewrite my original integral, right, as A over x minus 7. And what was A? A was 4. And then plus bx plus c over x squared plus 4, where b is 2 and c is 1. So that's bx, 2x, plus c, c is 1, over x squared plus 4. Okay, now, we can't break this up further, again, because this is an irreducible quadratic, prime quadratic factor. And so I can't break this up. So we're not going to use partial fraction decomposition. We've already done that. This we know already what the antiderivative of this will be, right? If I let u be x minus 7, I get 4 over u. That's going to evaluate as the natural log of the absolute value of u, or absolute value of x minus 7, times 4. So we've got that. Here, if I let u be x squared plus 4, du is just 2x. Oh, I've got a 2x plus 1, not 2x. So it doesn't work. How do I go about doing that? Do you remember what I have to do here? I have to split this up. I have to break it up. So let's take a look at that. Second page, a problem with the second page. So I want to focus on this 2x plus 1 problem here. I'm going to split this up. So I'm going to write this as, let's write the whole thing. So 2x over x squared plus 4 plus 1 over x squared plus 4. Okay, now, this one here. How can I do this one? Well, now I can do the u as x squared plus 4, and the du is what? 2x dx. So this becomes just the integral of du 2x dx over u, which is the natural log absolute value of u, where u is x squared plus 4. So we've got that. What about this one here? Anyone know where to go with that one? I can't, this is not a 1 over u because the derivative at 2x is not up there. I hope that you remember what this one is. Let's bring this down over here. And take a look at it over here, just by itself. I hope you're thinking of inverse tangent. We know that the integral, so we know that the integral of dx over x squared plus 1, remember, was the arctangent or tangent inverse function. Sorry, okay? But the problem is I have a 1 here, I need a 1 here. So how do I get that 1? I factor out a 4. And we've done this before. And you say, well, how do you factor a 4 out of x squared? Well, I'm going to have x squared over 4. All right, in the bottom. So if I distribute that 4 back through, I'm going to get x squared plus 4, right? Now I want you to note that this x squared over 4 is x over 2 all squared. This 1 over 4 can come out, and so I have 1/4 integral x over 2 squared plus 1. Now I'm of the form, right, except I need a u substitution, right? So what do I need u to be? I need u to be x over 2, which again is just 1/2 x. And what's du then? The derivative of u with respect to x is 1/2, so du is 1/2 dx. I've got a dx here. Notice if I multiply both sides by 2, 2 du is dx. And so my integral becomes 1/4 dx is 2 du, x over 2 is u squared plus 1. Now this 2 can come out. 2/4 is what? 1/2 du over u squared plus 1. And now we know we're in the exact form, and so I get 1/2 tangent inverse of u plus c, which I'm going to write as 1/2 tangent inverse of what? U was what? X over 2. Okay, so with that, I now know what my last integral is. It's arctangent. So I know what this is, know what this is. So what's our answer? Let's bring it all the way down after this analysis. Write it down here. So what's the antiderivative of this? This is 4 natural log of absolute value x minus 7. Okay. Plus what? The antiderivative here was natural log of u, where u is x squared plus 4. And natural log absolute value of x squared plus 4, I'm going to write it as just x squared plus 4 without absolute values. Am I allowed to do that? Could you write the absolute value bars? Yeah. Could you do it without? Yeah, because notice x squared plus 4 is always positive. So I don't have to put the absolute value bars. If you put them there, it's okay. And then plus what? The last integral here, which we evaluated, is 1/2 arctangent of x over 2, plus our 1c for the, combine all the constants in all those integral or antiderivatives, and we are set. All right. So you can see the wrinkle. When we have quadratic factors, sometimes this inverse tangent function, appears. Okay, sometimes it doesn't, but sometimes it does. So there we have it. Okay, one with a quadratic factor. Now, I'm going to stop here. In the next video, I'm going to do sort of a very challenging one. So it will have quadratic factors in it, actually more than one. So we'll see how that would look. And again, these can be obviously much challenging, but the ones we've done so far are the ones I would expect you to be able to work, you know, on your homework and in the test. So make sure that you practice those homework problems. But next video we're going to look at a very challenging one.